All right, yeah, welcome back. Now we want to look at performing machine learning on our data set acquired, on our features. We want to use our features, which our PCs we acquired uh, to classify the two disease, Fragile X and Williams Buren. So what to use? How many? What accuracy can we get? How many accuracy can we get? How can the model help us to classify them? So this is our previous features we acquired from R, component 1, 2, 3, and like that. So this is our target variable, okay, which we added, okay, according to the observations. So you can do this on this. You can also test your analysis, your result on the other PC, which we did in past. I've not done that, so you can do that and see which one is better for you. So I think Harris seems to be better for me, but you can also try and run it and see which one gives you more accuracy, higher accuracy. Okay, so you can stay to that. You can stay with that. But for me, I think I'm okay with this from R. All right, so because their score is not the same, you can see that their score is not the same. So, but at least we have 11 there, so which is okay. All right, so let's continue. We want to see how we can compute a SVM support vector machine to run this now. Okay, let's go ahead and do that quickly in R. So we have loaded our R. So we are going to load our. I save it as selected PC. You see now, okay, I call it selected PC. That's the file name, the CSV. All right, I'll save as CSV file. Okay, just a file, save as. Okay, select CSV file here. All right, so that is what you do. Just save it in your directory. Then you create your working directory, or you just set it from here. Set it here, session, working directory to source file location. All right, so that is already set here. So now you can run the library, run the ggplot for plotting, caret for to do classification and regression. Then this for SVM. All right, so you can just run this together. All right. So it's loaded now. So we can now load our data set now. We call it PCA data. That we want to create an object called PCA data. We want to assign we want to read our DC from our folder. We want to read it to here. So we just click here and run. So it's read. So you can look at the dimension here first. Let us say maybe just dim PCA data. So 120 by 61. All right. Should be 60 actually, but because we having a heading there, or so we can glimpse as well. We can glimpse. Okay, let me see if I can. Let me include library tidyverse. For data manipulation. Okay. All right. So let me see if I can glimpse now. All right. PCA data. Okay. All right. Okay, we have 1 to 12. Why showing this one? So this is our data set. Let me see. Oh, okay. I see what the problem is. So there's a problem here. Okay, don't worry. Let me correct it. I made a mistake there. So let's just it's not in my folder. I have different one in my folder. So just copy this here. I paste it. This selected PCA is wrong. Okay, this one is not correct. I rename it. Let me close first. Yes. Okay, this one we are using now. So that's what the problem is. So let me just rerun again. Right, so let me glimpse again. Okay, PCA data. All right, so this is correct now. So all right, so that this is correct one now. Now this one we are using. Now our target variable is disease. You can see that this is a factor variable. So we have not set it as a factor anyway, but at least it's for now it's a character variable. So all these other ones are double. Okay, total of 120 rows, 12 columns, which is correct. All right, so now this is we're just trying to see what we have there, the structure of our data. That's why I glimpse. All right, so now let's now go ahead and see. Let me clear screen. Right, so can slow this one down a little bit. Okay, so now let us now that we have our data set now, you can set a seed here, okay, for reproducibility, just that you can have the same result when we run. You can have the same so that it will generate a different random number. So now let's create a training data, okay, and testing data. So we want to partition our data set. Let's call it intrain and create partition here. Y as factor, PCA data disease, okay. I'm trying to partition, okay. This one is our disease variable is our target variable. So we are using 70 to 30%. All right. So let's run this line of code. But the partition the data is partitioned. So we are assigning 70% to training, right? Then the rest 30% to testing. That's what we are saying here now. So we say training equal to PCA to in training, okay, then the rest minus in training. So which means whatever we have here now, which is 70%, we are assigning to this 70% now. We are assigning to the first one, which is in training here, right? We run it. Then the rest, which is minus in training, 30%, we are assigning to testing. So we have 70 training and 30% testing. All right, so let's now make it this training factor as a factor variable now, so that I can use it to factorize our data. So this one is not necessary, but it's a good coding practice. All right, so then let's train our SVM model now. Let's call it SVM model. You can call it any name you like. So, but I prefer SVM model. So let's call this function SVM from this package E1071. All right, SVM. So our disease is our target variable. That's what we call here. Then we want all. That's why we say dot here. We don't want all. We can just say plus PC1 plus PC2, PC3, PC4, PC5. You select the PC you want. All right, but we want all. That's why I say all except disease. So now data is training. We are supplying train as a data. Our data here to train. All right. So color is a disease. All right. This is not important. Okay, not important. I remove this. So, but kernel linear. So linear kernel. So you can try radial as well. All right. But the epsilon is 0. So you can run this line of code and see. Okay. So let's see the result of our model. I've created the model now. Let's see the result. Let's see SVM underscore model summary. Okay, sorry. SVM model. Okay, so let's see if we have a summary here. These are our parameters. So we say parameter SVM classification. We are trying to see classification which is correct. It pick it by itself automatically. Then kernel is linear, cost is 1. All right, number of support factor is 30. So don't forget support factor means number of factors that are supported in this line. Total is 16 here, 16 here, 14 here, making 30. Okay, that are touching the edge of the supports. Okay, of the hyperplane. The number of classes is 2, which is fragile X and Williams. Now we can recognize that in string form. All right. So let's go further now that you have seen that. So we can now prepare our control matrix. All right. Can do that here. So bring this down. Prepare our control matrix now. Okay. So let's say we want to prepare control matrix for we don't really need this actually. We don't need this actually, but just let us test first. Let us test from here first. We can test for here for training. Okay, we prepare. We create a prediction. I have to predict, but we should jump to it straight. Okay, but let us start from here and test here first on our training data first before we do a proper creating. So okay, predict SVM model. Our model is called here. Our training data set is called here. Then we create a tab table predicted. So this, then we show error. So let's create this now. Then let's now run this. Our error is 0.107. So, but we don't really need this actually. We don't need this actually, right? We don't need it. I can remove that. What we need is so let us first predict now. We train it the data. So we want to use this particular function here. Okay, it will give us everything we need at once. So we create a pre-trained data. Predict our model, new data is training, which is the same thing we did here. All right, don't forget that. So we want to do it proper here using this function. So we just create a pre-trained data. So this is what I want to train. I want to first test on our training data first. So we do that here. So we run it together. So we have our look at it here. So the statistics of what we have now. So we have our control matrix here, fragile X, Williams. Don't forget, I showed us how to calculate this before. Don't forget that during our introduction. Okay, we did in the slide. We have this true positive, and false. This true positive, true negative. Okay, this diagonal, they are true. Right? We sum it together over total of this. This one is false positive, false negative. So, but we have to sum together everything. This diagonal and we add together divided by all of them. Okay, that is what we did. You can do that by yourself manually to get this. Okay, you need to have this. All right. If you have okay, let's say we have let's calculate calculator. All right. Let's say we have 37 plus 30, 37 plus 38, 37 plus 38 equals to 75. Okay, let's keep that in mind. 75. Now let's now sum together. Let's sum together everything we have here. We have 37 plus 38 plus 9. This plus this is 9. Okay, 9. So 84. So 75 for 84. That's what we have now. So let's say we have 75 divided by 84. We have 0.89. You can see here 0.8928, 0.8929 approximately. So this is how you calculate your accuracy. All right, don't forget that. So that should be good enough for you to go. All right, now we have gotten our accuracy here. Now this is what we need. Right, you can additional information kappa computer interval here. This lower bound, upper bound. All right, so you can now go to sensitivity, specificity. Okay, precision. This precision. All right. So these three information are very important also. Okay, they are needed, so you can keep them for your analysis. So we are going to bring them out later. This one going to bring them out later. Okay. All right. So though you can extract them manually. All right, if you want. Okay, but at least we don't need that. So let us see how you can for the training only. For the training only, this is our training. But the data we really need is testing, not training. Right? The one you present, you put in your manuscript or test is whatever is testing data, not training data. Training is to train to see how it will operate in training. So, but the one that I'm going to show in your test, in your manuscript or your journal, whatever is testing. So we are going to run this now on this line again. This is our testing data now. So this is testing data, all right, not the training data. So this is our new data testing disease. So let's run this line and see the result. So it's 83.33. Okay, so that is what we got, 3.33. So that's our accuracy now. This is our accuracy. The former one is not our accuracy because that one just is training data. So you cannot present that as accuracy. That is wrong. So our accuracy is 83.3. So if you want to improve on the model, you can improve on the model. If you want to improve on the data, you can improve on the data. You don't want to go into details about that for now. So you can just do with this. You can transform your PC further to get higher accuracy. All right. Maybe other classifier can help us. Other algorithm can help us to do that. Maybe can help us to have a better accuracy. But for now, let us do with our 83.3%, which is good enough. It's not too bad. All right. In classifying this disease into Fragile X and the Williams variant. So we're able to classify 83.3% for our testing now. So this can be copied. So this our sensitivity is 88.89, specificity is only 7.78, and our precision is 80.0. So we also have F1 score here, but it's not showing. But you can generate that manually. Okay, you understand? So because if you assign this, if you say we assign this now. Let's say we say this one is our metrics. Let's say we call it metric. Let's call it metric, for example. So if you run this line, we assign it to a variable called metric. So we run this line now, for example. If you say metric dollar metric now dollar, so you can see it giving you some information here. All right, you can see. If you say by class, if you say view by class, for example, you run this line to give you all the one by one. We give you the, let me just expand more, right? And you run here. Let me run again. Now by class, so it's giving you sensitivity, specificity, precision, recall. You can see now F1 score. This is F1. So the complete details, everything is inside. So it's the same thing. You have data you see have here anyway, but it gives you additional information. Okay, give you precision here. Okay, which is the same thing as what we have here in a what they call it now, positive. This one, this is precision, right? Here we have precision here. This one is precision. Now see the same thing we have here. All right, don't forget. We see have here repeated here, but it's here. Same thing here, same figure here. But this record here is our sensitivity. Okay, it's called recall. Sensitivity is called recall. Okay, that's what we have here also. Okay. All right. Then we have what they call F1 score. This F1 score here. So these things are very important, and we need to copy this out later and arrange them in the table. I'm going to do that actually. I'm going to keep this score. I'm going to arrange them in a table in a Microsoft Word so that I can compare the result from each of the different algorithms that we have, so that you can see the difference, what we generate for each of the. So let's keep this in mind. I will towards the end I will do that so that we can be able to compare our results. So that is that for today. So let me now plot the hyperplane scatter plot now for this particular SVM. So our PCA score is this, so that our disease, our target variable, we factorize it here. Okay, this one, this one. So just this is what you have here, right? This is what you have here. Let me just press enter from here, okay, so you can see. All right, good. So what we have here now. Okay. All right. So you can see clearly now. So it's okay now. Then we can run this line of code. So we want to. So we run this line. Then we move further. So we want to build the scatter plot distribution, the classes by color. So color is disease now. We call the comp1, comp2. We are basing on S and Y axis. We are going to collect the first two components, right? Okay, so they may not be the best component, but at least they have the highest information that we need. All right, so we can just run everything together here. All right, so we want to increase the size to 3, and want to color by a scale. This fragile red, this one blue. All right, so that is our color. So you can change the color if you don't like that one. So we run this. All right, so then we now I'll assign a straight line. Want to run a slope, a line on it. So this we assign to P, to P now already. This ggplot now. You can just be the ggplot. This is very simple to do. So you can just follow the same. This is our data set. Okay, data is data set. Aesthetic is our x-axis and y-axis. This is a component 1, component 2 for x and y-axis. The color is disease. Okay, so we'll separate by disease. That's what it means. Then our size is geopoint. We have the geopoint will be scatter plots. Our size is 3. The point size, that's what it means. So if you say 2, it will be so small. So let's use 3. It's okay. We want to color by manually. But we want to assign a different color manually. So Fragile should take red color, while William should take blue color. You can change the color as you want. Okay, so that's why I left it like that, so that you're able to control your color. If you have more than 2, you can control the color, maybe red, blue, green. All right. So let's also assign we create another P again. P equals to this P plus geo line. So we want to assign a line, okay, to separate the 2 of them. So we run this line. All right. So you can now print. You can call this P now to print. So okay, just run this P now to print our. It's running. Okay, let me just adjust it a little bit so that I can see what we are doing. So you can see it here. Can you see? So that we have disease fragile here, so you can zoom and see properly. Can you see? This is what you need. Okay, your manuscript or thesis. This is comp 1, comp 2. So this disease fragile X William. So this is scatter plot. So this hyperplane, you can improve on this if you want to improve on it to expand further. So but you can see the factors on this line. Okay, this line. So you can see we have more red on the lines than the blue. Blue does not touch the line. So but if we look at the major hyperplane, okay, you can see that we will see that there will be some blue on the line and some red on the line also. But now we don't need to set ourselves for that. We don't need to. You want to distribute our and separate them into 2. And what we just did here, so you can see it's properly separated. And that is our fragile hairs is here, our Williams here. So you can see the difference in the scatter plot. So I think that is that for today. So thank you so much for listening. I will see you in the next class. We'll be building another machine learning algorithm on this particular our data. Thank you so much. Thank you.